Okay, today we are talking about review of yesterday first, and yesterday's was this. What kind of a function is that? Exponential. Exponentials have an x in the exponent, and one of the problems yesterday had an x down here also. It had an x in the exponent, but also had an x down here somewhere. That's not allowed. Just to clarify, when you're asked, is something exponential, if it has an x in the exponent is one of the things you look for, but it can't have an x anywhere else. It has to only have an x in the exponent. Okay? So that was just a small point of yesterday that I didn't explain to you well. All right, so this is the starting value. Do you remember that? So if I had like 500 deer, I would put that as the starting value. Okay, and then this b was oftentimes written with like a 1 plus something for growth or a 1 minus something for decay. So let me give you an example. Do you get that that's the situation for a population of 500 deer, and they are declining by 3% per year? Does that make sense to you? All right. Could this be money? Could be $500 invested in an account that's actually losing 3% per year. Yes, you don't usually sign up for that on purpose, but sometimes your accounts do lose 3% because you had a bond fund which is supposed to grow a little bit, but then bonds go down in value and interest rates go up, and so you might lose money. That could happen. All right. Here's a typical problem from yesterday. Y equals AB to the x, and if this is the graph of it, and that's the starting value at 3, I'll put it as 0, 3, because the starting value would always be 0, whatever. Then another point on it is, let's say 8, 12. Would you figure out for me what the equation is? That's exactly the kind you did yesterday. You already know A if you know what you're doing. B you can solve for. All right, I'll give you a second to try that one while I take attendance here. Okay, here's what you should have done. I'm going to do it fairly quickly because it's a review problem. Y equals, the A is the starting value. Right there tells me that it's 3. 3 times B to the x. Don't know B yet. I put in x and y. How do I know x and y? From that. That's x being 8 and y being 12. So I have 12 equals 3 times b to the 8th. Divide by 3 on both sides. 4 equals b to the 8th. I know some of you might have been stumped there. From there, you just need to put it to the 1/8 power. And I know that you're not going to have it memorized what 4 to the 1/8 is. But do you get that you got the b alone, and the answer is 4 to the 1/8, whatever it is? It's some decimal. It's like 0.379 or whatever. Actually, it has to be bigger than 1, like 1.259 or I don't know what. But you could use a calculator if you had to. Now on the test, the toughest one we might give you would be something like this: 8 to the 2/3. I don't know if you remember doing fraction exponents, but you break them in 2 parts. 8 to the 1/3 to the second. Do you get how there's a 1/3 part and there's the 2 part? 8 to the 1/3 means the cube root of 8. What is that? 2. And then 2 to the second would be 4. So the final answer on that is 4. 8 to the 2/3 would be 4. Because you do the 1/3 part first, 1/3 of 8, or 1/3 root of 8. Sorry, 1/3 power of 8 means 8. The cube root of 8, which is 2, and 2 squared is 4. Okay, let's move on to a different. Oh, wait. I just figured out what b was. I got to back up. So now I'm not done. I thought for a second I was done there. But I figured out that b was 1/4 to the 1/8, no, 4 to the 1/8 power. Now, how do I finish the job? The job requires you to write out y equals ab to the x, except we now know a. A is 3. And we now know b. b is 4 to the 1/8 to the power of x. Do you get that that's 1/8 x, or it could be x over 8? Either way would work. Get how this is being put to the power of x, which really means these get multiplied. So you could say 1/8 x or x over 8. Yes, sir?
Could you simplify that down to 2 squared and have that?
Wait, hold on. Why would it be 2 square root of 2?
Because, sorry, somehow simplify it to 2 and do something with that root up there? Or
Not that I know of. I don't know where you're getting your 2 from.
because 4 is the square of 2?
I don't think so. I mean, I know we could rewrite this 4 as 2 to the 2nd power, I guess. And then I could say that's really 2 to the 2/8, which would be 2 to the 1/4 power, but that doesn't really help me very much. Okay, so bottom line is, this is it. We are done. You can leave it like that. If you have a follow-up question to ask me, ask it during, that is simplified. If you want me to clarify it more, ask me later. All right, we're going to move on to new stuff for today. Well, yeah, I need to know what the growth and decay look like, because we're going to kind of build on that. So that was growth. One like this green one, that would be decay. Do you get the difference? Over time, the one's growing, over that time, the other one's shrinking. You get that? Okay, well, this growth one, that looks kind of like this, that could be almost anything. Y equals 1 times, because I started it right here at the kind of the normal starting position of 1, times 3 to the x, or 1 times 4 to the x. It doesn't really matter much what this number is right there. As long as it's above 1, it's going to be growing. And then just the bigger it is, the steeper it gets. So if this is 1 to the 4th, then y equals 1 times 5 to the x, that would maybe be even steeper. And they just get steeper and steeper the bigger the number gets. Okay? There's a special number, though, that we can use in here. Instead of 2, 3, or 4, or 5, or whatever, it's e. Now, you may not remember what e is, or maybe you've never even been told what e is. But e is a special thing, kind of like pi. Pi is 3.14. You know that one, right? There's a few other big numbers that you're expected to know in your history. There's e, there's phi, and there's pi, and there's a few others, but I'm going to stick to those 3. Pi is 3.14. Phi is 1.618. That is the perfect number, the golden ratio. That's that number that I've showed you before with this stick, where the golden ratio appears on the human body so many times it's ridiculous. And this is in that ratio. So, for instance, if I hold it like this, you can see that from my shoulder over to the end of my other arm, compared to the yellow part that goes from my shoulder to the end to the tips of the fingers there, that is a ratio of 1.618. And if it was off, my arm would be like way longer than it's supposed to be. Okay. If I hold it like this, every human being has a stick like this, so to speak, in that it's your height, and mine's not thrown off by the height of my shoes right now. Okay, but I'll lift it up a little bit. That's where my belly button is. You have to trust me on that one. But that is the perfect ratio. It's in just the right spot. If you look at a person and their belly button is like way too high, it's like, whoa, it's really kind of scary. You know exactly where it should be, just because, like, you could draw a person, and I guarantee you, if you just, sketched a person, you'd know exactly where to put the belly button in, and it would be at the ratio point of 1.618, because that's where it is. And if you do the width of your face compared to the height of your face, and you divide them, the bigger divided by the smaller, it's 1.618. If anybody's got a super tall face, like really skinny face, it would stick out to you, right? It'd be like, oh, that's kind of strange. That's because the ratio's off. It's not 1.618. Now, is everybody exactly 1.618? No. But the closer you are to that perfect ratio, the more beautiful the person is. In empirical measures, like when you compare people, and you have people in a survey, and they're like, how beautiful is this person on a scale of 1 to 10? The people that have the ratio the best also get the highest ratings for beauty. They have some pictures that are pretty amazing of the beauty mask, they call it, which is where everything is exactly perfect ratios. And nobody fits into it perfectly, but the closer you are to it, the more pleasing it is to the human eye. So, all right, anyway, that is a cool ratio I wanted to remind you about, phi. But then there's E, and that's what we're using today. E is like the banker's favorite number, because it's used to compute perfectly compounded interest. I can show you that later, but it takes a long time. But for right now, I'd just like you to know it's 2.718 approximately. E is about 2.718. So if I say y equals e to the x, it shouldn't be too scary to figure out what it is. If you just memorize that e is about 2.7, If I say y equals e to the x, I've really pretty much said y equals 2.7 to the x. And what's the starting value on it? Not 2.7, 1, because I could put a 1 times in front of that, right? So it has a starting value of 1, and it has basically growth. So it's basically just a growth graph again. It just looks like this. It just happens to be a special number. Now, what's really special about it is when you get to calc. When you get to calc, you'll understand that when you're finding derivatives, derivatives are a slope at a certain point, and the derivative of this comes out to something really cool. The derivative of the line y equals e to the x is something awesome. All right, you'll understand that more when you get to calc. So for right now, all I need you to know is that y equals e to the x is this. It's pretty much just a growth function. So if I show you this, you should go, oh yeah, that's growth. It's 2.7 about, so it's like this. One of the keys you have to understand is you don't really need to have perfect graphs in this unit. You have to have sketches. Because what they're going to ask you for is the limits. The limits just means in the long run, where is it headed? Do you get in the long run, this one is headed towards infinity? Do you get as I go way to the right that this one's headed towards infinity? Do you get that? Okay. Do you get that if I make it the other way around like this and make it a decay, that in the long run, oh, I should be careful at this. People do get confused on this. Is this one heading towards 0 or is it heading towards negative infinity? It's heading towards 0. It's going to get closer and closer to 0. See how it's leveling out here? It's because there's like this imaginary asymptote line right there, and it's just going to get closer and closer and closer, but never touch it. Okay? So the limits are that's important. Do I have to know exactly, the numbers? No, we're not doing a graphing unit for a while. This is just general sketches. All right, so if I told you two of them, there's the blue one, and then there's this green one. Which one's decaying faster, the blue one or the green one? The blue one. So that would be like, let's say, a 50% decay rate versus the green one might only be a 30% decay rate. As long as you get the difference between the two, you're good. All right, so how about this one? Let's say I've got growth. Let's say I got the blue one growing, and let's say I've got this red one growing faster. Okay? Which one of these has a growth rate of E versus which one of these has a growth rate of 5? One of them is going to be y equals 5 to the x. One of them is going to be y equals e to the x. I'll use a different color I haven't used yet, maybe green. Which one would have to be the e to the x? The red or the blue? The blue. Very good. Because this one's the smaller, because 2.7 is smaller than 5. So this one would have to be the blue one, and this one would have to be the red one. All right, it's just like comparing the two. You don't have to know exactly where they go. You just have to know one's steeper than the other, that you have to be able to tell which one's which. All right, now let's talk about these two. If this is a typical question for today on your homework, it'll ask you to tell when is e to the x. Oh yeah, that's the blue one. Let me use the blue for that. Color coding is known to be a good thing. So the blue one, when is e to the x greater than the other one, which is the red one, which is 5 to the x. Now note for a moment, do you get that these both have a 1 times in front of them? Their starting value for both of them is 1. That means this spot right here, they both go through the same exact spot at 1. Do you get that the blue one is sometimes above the red one, and the red one is sometimes above the blue one? What this is asking for is when is the blue one above the red one? When is the blue one above the red one? Would you agree that it's not in this zone? In that zone, the red one's above the blue one. When is the blue one above the red one? When it's negative, how do you say that in math? I'll give you a hint. It looks like this. From negative infinity to 0. Perfect. That's when the one function was bigger than the other. All right, I want you to sketch these two functions. Y equals 1 minus 0.3, 30% decay. Y equals 1 minus 0.5. Make this one solid. Make this one dotted. Make a quick sketch of both of them. And then, after you've made the quick sketch, tell me, when is the solid greater than the dotted? Also known as, when is the 0.7 to the x bigger than the 0.5 to the x? And these, by the way, should really have a to the x power on them. I forgot that they're exponentials. Sketch them both. Sketch one solid, make one dotted. Try to figure out when the one is above the other. Okay, so hopefully you made a sketch, and your sketch should have been like this. A solid line going down about 30%. I don't know what that is, but I know if I make it solid and I make it going down like that. How steep? I don't know, and I don't really care that much. All I know is that it has to be different than this other one, and this one needs to be steeper and dotted. So you didn't have to do it dotted if you, as long as it's underneath the other one. Okay, now, when you make one of them dotted and one of them solid, it is easier to tell them apart then. The solid one needs to be bigger than the other one. Where's the solid one bigger than the other one? Here's where it's above it and therefore bigger. It's in this little zone. How do I say that officially? 0 to infinity. Raise your hand if you had that one right. Good, that's most of you. All right. So if we, I've handled that graphing part. There's only a few parts left that you really need to be able to handle. There's a new function in town. Besides that e to the x, we're introducing another one. You'll have to wait for your question for a minute. Y equals e to the x is a big one, and that's the one we just learned looks like this. Here's the new function. It's one of the big 12. There's only 12 precalc functions that are the important ones. They're so important that on the back of the textbook that we used to use, which, believe me, you're happy we are not using it. It had a lot of really, really tough problems that didn't make any sense even to the teachers. Anyway, this back page of it has the 12 big functions. Okay? I just taught you that one. Can you see it even from your seats? Those of you with good eyesight anyways. That's one of them. That's the e to the x function. Then there's this one. And it kind of looks like a sideways s. That's the one I'm going to teach you next. That one is called the basic logistic function. And it looks like this. It's got an e to the x in it, but it's kind of buried. It's L over 1 plus e to the negative x. What does it look like, though? This function's kind of cool. It starts out going up like it's going to be an exponential function. It's just going up and up, and then all of a sudden, something unique about the way this function is designed causes it to level off. Like that. Slide that over to be right. Good. And there's an asymptote at that spot. It gets closer and closer to this limit. What's the limit? It's whatever number is on top. So let's say in this case I make this like 18, then whatever number's on top is what the limit will be. So this will be like an 18. So again, you remember how I was saying I don't need you to be perfect on the graphs, it's just sketches? Do you get that this sketch, I should be a little better on this end of it, shows that it's going up closer and closer to that asymptote, but it'll never touch it. And then on this end, it gets lower and lower, but it never touches 0. So there's actually asymptotes on both sides. So that means it's got y asymptotes, horizontal, the y asymptotes. The y asymptotes are at 2 places, in this case 18 and 0. Which of those could change? The 18. The other one will always be at 0. But if you decide to make this 21, then this will go to 21, and then this will go to 21. That number could change. Depends on whatever's the top of that function. So if I gave you this function, I could ask you 2 important things. One is, what is the horizontal asymptotes? And it's this and 0. And the other important thing I got to ask you is, What's the y-intercept? Now, why does that seem important? The y-intercept is the starting value, see? And these are oftentimes used in population problems where you have like 7 tribbles. If you've ever seen Star Trek. Not everybody has a tribble in their backpack. 7 tribbles, and your tribbles are multiplying, growing, and all of a sudden they start leveling off in population. Why? Well, actually, tribbles in the movie would never actually stop multiplying, but this is going to level off. In the real world, do populations level off, or do they just spike forever? They level off. And if you have a population of deer in Minnesota, if they didn't stop multiplying, there'd be deer everywhere. They'd be like deer stacked on top of deer. Okay, so it obviously doesn't make sense that they go on forever. Populations follow this a lot better than they follow exponential growth, because the exponential growth goes on forever and never stops. In the real life, there might be growth for a while, but then it levels off. All right, so given all that I just said, if I gave you this formula on the test, could you make a sketch for me of what that would look like? Just to make a quick sketch. And tell me what the horizontal asymptotes are. And then this is going to be a little trickier part, but you should be able to handle it. What is the y-intercept? The y-intercept is known as the place where x equals 0. So break out of your slumber, grab your pencil, don't make me name names, and make me a sketch. And then tell me the y-intercepts, sorry, there's only one of y-intercept. Yep, you drew yours right. And tell me the horizontal asymptotes. Therefore, y equals things. Okay, this should have been starting down here, going up like this. There's an asymptote line like there. I kind of missed it though because I made it touch the asymptote line. It'll be at, never actually touch that line, and that line will be at 20. Raise your hand if you sketched it correctly. Good. Then your two answers were y equals 20 and y equals 0. There's an asymptote down there. A lot of people forget. It goes like this. Then, what is the y-intercept? The y-intercept is where x equals 0. Look in the equation. There's the x. What if I make the x equal 0? Then I go and put a 0 in there. Negative 0 is still 0. E to the 0 is equal to 1. 1 plus 1 is 2. 20 divided by 2 is 10. The answer is 10. Do you get how you can't just see the starting value super easy? But we just figured out the starting value. The starting value is where it's the y-intercept. The y-intercept is where x equals 0. When I stick in x equals 0 here, I ended up getting a 1. E to the 0 is 1. 1 plus 1 is 2. 20 divided by 2 is 10. So your answer for the start or the y-intercept is 10. It's not nearly as nice as this kind, because on this kind, you can tell the y-intercept's really easy. The y-intercept is where x is 0. See, if I put a 0 there, this whole thing disappears, and then the start value is right there. Okay. It's a lot of stuff we've covered. Yes?
Is it like a coincidence that it's calculated at 0?
No. Well, I think, okay. Yes, it is a coincidence. We cannot just assume that the answer is always going to be halfway in between. It totally depends on the problem. I'll give you another one real quick. Y equals 35 over 5 plus 2e to the negative 2x. I'll just ask you on this one, what's the limit to growth? What's the highest this thing will ever go? 35. So what are the two asymptotes at? 35 and 0. Good. And if I were to ask you for the y-intercept, you would plug in what? 0 for what? X. Y-intercept is where x equals 0. Try to figure it out in your head. Put a 0 in there and try to reason it out. I'll do it at the same time. I'll pause for a second while we try to figure out what happens when we put in x equals 0. All right. So we put in a 0 right here. You get this is 0, and then e to the 0 is 1, and 1 times 2 is 2, and 2 plus 5 is 7, and 35 divided by 7 is 5. Raise your hand if you had a 5. All All right, awesome. So 5 is my Y-intercept, also known as my starting value. It is a coincidence that that was a 5. That didn't happen to make that the answer. Okay. All right. We've covered a lot of what you need to know. One more last little thing that's kind of important. If I had this, y equals e to the x, do you get it would change it a lot if I put a 2 right here? What would that do? Vertical what? Stretch with a factor of what? 2. All right. Think harder. What would that do? Horizontal shrink, factor of 1/2. Very good. What if I threw in an extra that? What does that do? Right 4. What does this do? Up 8. All right, good. Do the orders matter? Yes. If you had to do this whole problem, you would start on the inside. It's my recommendation. Technically, you can do it from the outside in also, but start on the inside and you do it in the reverse of normal order. You remember that? And then when you're done with that, you go to the outside, and this will always be first, and that will always be last. Okay, so we'd start on the inside, and we have these two things in the right order. Normal order is the multiply comes before subtract, so that would actually be first. This would be second. Then we move to the outside. This would be third, and this would be last. That make sense? All right. I think we covered everything we need to know. I'm going to hand the worksheet out and do the first couple problems with you, so I'm just going to pause the video while I hand it. Okay, let's do the first one together. Numero uno. It says, determine a formula for the exponential function whose graph is shown here. Okay, so it gives me this graph, and it gives me this point. Oh, that's the good. That's the starting value. It's 0, 2. All seems normal from here. Y equals a b to the x, and so the start value is 2, so I put a 2 here. Piece of cake. Easy peasy lemon squeezy. Except now all of a sudden, I look at the point they gave me. Please don't talk right now. The point that they gave me is at 1, 2 over e. And I got to put that in somehow. Ooh, that's weird. Well, it's still giving me an x and a y, right? I mean, this is x and this is y, so I'm going to stick them in for x and y. X is a 1, so I put a 1 right there. And that's kind of nice because b to the 1 is just b. And the y is 2 over e. So 2 over e equals 2 times b to the 1, which is just b. Well, that's almost solved. I know you might be tempted on e to put in 2.7, but remember, that's an approximation. You'd end up rounding your answer. Even though you may have memorized that e is 2.7, 2.718 is even better. It's actually a decimal that goes on forever, like pi. So we really don't want to round it. We want to just leave e in the answer. So how can I get b alone? I multiply by 1/2 on both sides. Could I have divided by 2? But yeah, but then it'd be a fraction divided by fraction. That's kind of a pain. So the 2 and the 1/2 cancel, so b is alone. I figured out b, and the 2's cancel here. 2 cancels the 2. It's 1 over e. So then, the goal was to be able to take this and write it with a and b figured out. I figured out a right away. A was 2. B I just figured out. B is 1 over e. So I'm going to rewrite it now. Y equals 2 times the b, which was 1 over e, to the x power. Now that may look really strange, but it is the right answer. It's just got an e thrown into it. You have to be able to deal. All right, moving on to number 2. Number 2 is just asking you for what's the difference between the e to the x one. Hopefully you remember what that kind of looks like. It's your basic growth kind of deal. And e to the negative 2x. There's obviously two things different. There's a negative and there's a 2. Do you remember that that's a flip? And then what's the 2? Horizontal shrink. So if I sketch this, it looks like this. If I sketch this, it's a flip this way, so it's going to be like that. And then it's a stretch, or sorry, a shrink of 2, which basically means it just kind of squishes down a little bit. So it's just a little more squished. And it doesn't, I would never even be able to tell the difference between the two sketches. So the stretches like that, you're really not going to get that marked wrong, because I can't even tell the difference. These are sketches. But do you get how this one is basically going up as you go from left to right, and this one's basically going down as you go from left to right? so their limits would be different. All right, so describe how to transform the one into the other. Well, I made my sketches. Well, how about a description? Number one thing is I do a horizontal shrink factor 1/2. And the other thing I do is a reflect. Does the order of these two matter? Actually, it doesn't. They're both multiplies, so it doesn't matter. Reflect, and it's left-right, so that's over the y. Okay? That's how you do problems like 2. You may skip number 5 to save you a little time. You may also, turn the page, skip number 12. Skip number 12. Those are the kind where you graph both of them. Go ahead. And you see where the one is above the other, but you could skip number 12. Now look at 14 and 15. On that, you're supposed to prove that 2 of the 3 are identical. Look at A, B, and C. 2 of them are the same. Just look at them for a minute, and I want somebody smart to tell me, which do you think are the same? A and B, or is it B and C, or is it A and C? A and C are the 2 that are the same. You're right. So write them out next to each other and say equals. That won't be a proof, but I'll at least say, here's what I start with. 3 to the 2x plus 4, you're saying that that's equal to 9 to the x plus 2. Then if you're doing a proof, how you prove something is you actually keep this side the same, and remember, you can't mess with one of the 2 sides. I would always leave the side on the right, leave it alone. But the left side, I got to slowly work this thing, do some algebra magic until it turns into 9 to the x plus 2. Now, I'll give you a big hint. The first thing you should do is factor a 2 out of there. Once you factor the 2 out of there, it'll become pretty quickly apparent why they're actually equal. This number 16, 17, 18, 19, you may skip number 19 in that little block. 16 through 19, you can skip number 19. 20 and 21 are exactly the same as what you did on last night's homework, where they give you a starting value in the chart. Remember where the starting value is? The starting value is the same as the y-intercept. Where's the y-intercept? Where? X equals 0. Very good. Look up at number 16. That's the one I want to do with you. Let's do number 16 together. Number 16 says f of x, which is the same as y, equals 12. Ooh, I know this kind. That has a limit of 12. Over 1 plus 2 times 0.8 to the x. Now, you know what these look like. Don't overthink this. You don't have to have a perfect picture. You know they generally look like this. You could draw that for pretty much all of them. Now, how high does it go? Well, that depends on the picture. This one goes to 12. So I can put my dotted line in and say it goes to 12. There, good enough. That's a sketch. Now, find the y-intercept. Finish this sentence. The y-intercept is where x equals 0. So I stick in a 0 right there. And if that becomes a 0, then it's 0.8 to the 0. 0.8 to the 0 really becomes what? 1. And then 1 times the 2 makes 2. 1 plus the 2. 1 plus 2 makes 3. 12 divided by the 3 makes what? 4. In this case, that's a 4. The y-intercept came out to 4. If you want to make that 0, 4, that'd be great. You don't have to. You could say y-intercept is 4. Now the horizontal asymptotes. There's 2 of them. There's that one. Horizontal asymptotes. Are the x's or y things? Y. The horizontal asymptotes. Y equals 12. And the other one down here at y equals 0. That's the answer for number 16. Okay, hope that helped. Now, remember that I promised you I'm going to grade tomorrow no matter what, even if I don't have time to teach the full lesson. So make sure you got homework done for the last few days, and I'll decide which ones I want to grade tomorrow. That's all I got for the video for today.